Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, here we have the problem sets for lecture 97. I'm going to start on number 1. How many electrons are in a charge of 1 microcoulomb? That one is not too bad. So for starters, what is 1 microcoulomb? So 1 microcoulomb is equal to 1 times 10 to the minus 6 coulombs. So, and we know that 1 electron has a charge of 1.602 times 10 to the minus 19 coulombs. So it's just a simple matter of dividing this into this. And if I do that, if I have 1 times 10 to the minus 6 coulombs, divided by, which is the same thing as multiplying by, 1 electron per 1.602 times 10 to the minus 19 coulombs. Plugging that into my calculator, I get 6.242 times 10 to the 12 electrons. So E minus, make that 1 electron equals. And that's pretty much all there is to it. So that's problem number 1. All right, problem number 2. What are the electrostatic and gravitational forces on an electron in an atom of hydrogen? Assume the mean separation of the electron from the proton is 5.3 times 10 to the minus 11 meters. Look up the other numbers. Okay, this is pretty much very similar to what I did in the actual lecture. You should look back on that in lecture 97, and that will guide you through it. There we took the ratio of the gravitational force, the electrostatic force to the gravitational force. Here we're just going to calculate each of them all by themselves. So, where do we begin? Let's start with the force, the electrostatic force. And I'm not going to worry about directions here. We'll just calculate magnitudes. It's going to be K times, call it Q minus, times Q plus, divided by R squared. Well, K is Coulomb's constant. That's 9 times 10 to the 9. We won't worry about the units. They're Newton meters squared per Coulomb squared, times the charge of the electron and the charge of the proton are the same, so we can just square one of them, 1.602 times 10 to the minus 19 squared. And we'll divide that by the distance given for the radius, which is 5.3 times 10 to the minus 11. So 5.3 times 10 to the minus 11 squared. And if we plug that into our calculator, we should get for this one that it is 8.223 times 10 to the minus 8 newtons. Right, and we can do the same calculation for the gravitational force using Newton's universal gravitation. F sub g is equal to big G times the mass of the proton times mass of the electron, also divided by R squared. The gravitational constant is 6.67 times 10 to the minus 11. That will be times the mass of the proton is 9.1 times 10 to the minus 31 kilograms, and we'll multiply that times the mass of the electron, which is 1.67 times 10 to the minus 27 kilograms, and we'll divide all of this by, again, 5.3 times 10 to the minus 11 squared. And when we plug all that in, what do we get? We get 3.6 times 10 to the minus 47 newtons. And so if you take the ratio of those two, you'll get the 40 orders of magnitude difference that I got in the lecture. Okay, number 3, calculate the electrostatic forces on Q1, Q2, and Q3 in the figure below. Let K equal 1 and Q1 equal Q2 equal Q3 equal plus 1. Note these are vectors. So this is a vector problem. And we should start by basically drawing what's going on here. The distance from Q1 to Q3 is a distance of 5. The distance of Q1 to Q2 is 3, and the distance of Q2 to Q3 is 4. This, of course, is the famous 3, 4, 5 triangle. It's a right triangle. You should probably recognize it. Also, we're going to put the x-axis and the y-axis like this. So I guess you call those x hat, y hat directions. So let's start with the easy one first. The easy one is the force on 2, because it's going to be contributed only in these principal directions of, sorry, there's thunder in the background, in the I hat direction and in the J direction, right? So let's do F2 first, because that's pretty straightforward. So F2 will be equal to the force of 1 on 2 plus the force of 3 on 2. Remember, this is the principle of superposition, so we only have to consider each charge contributing to the net force on charge Q2. And so now I need to write F12. And F12, also we need to keep, I'm going to keep track of the directions here with the forces. So the force from 1 acting on 2 is going to cause it to go this way, since they're all positively charged, right? And so that will be a positive. But the force on of charge 3 on charge 2 will be acting in the negative y direction. So I'm going to just change the sign here. So since K and Q are all just equal to 1, this is really just 1 over, so F12, right, is 1 over this distance squared, so that's 1 over 3 squared in the I direction, or the x direction, the I hat direction. And the force of 3 on 2, right, again, will be minus 1 over 4 squared in the J direction. And so this is 1/9 I minus 1/16 J. And that will be our answer. Yeah, so that one is not too bad. But let's look at the harder ones are F1 and F3. So the force on 1 and the force on 3. Let's do the force on 1. That's going to be equal to the force of 2 on 1 plus the force of 3 on 1. Let's look at the signs of these. So 2 acting on 1 is going to cause the charge to go in the negative x direction, so we need to put a negative in front of that. And the force of 3 on 1, which is acting along this diagonal here, right, is acting in the negative x and negative y direction. So this also will be a negative. So 1 over 1 minus the distance between 2 and 1, that's just along the I hat direction. So that's going to be, again, 1 over 3 squared, or 1 over 9, in the I direction. But for the force of 3 on 2, this has the force of 3 on 1, it has an x component and a y component. And you can kind of think of this, if you want to, like if we knew what that force was, it's going to be the magnitude of this, right? And so the magnitude of this is just 5. Well, it really is going to be 1 over 5. So 1 over 5 squared, excuse me. The magnitude of this is going to be 1 over 5 squared, or 1 over 25. So I'm going to put minus 1 over 25 times. Now, if we take the magnitude and we multiply, we want to see what it is in this x direction here, right? We would multiply times the cosine. The cosine is 3 over 5. So that's 3 over 5 in the I direction, or x direction. If we knew the magnitude of this force and we wanted to see what it was in the y direction, right, we'd multiply it times the sine of this angle, right? So that's 4 over 5. So this is 4 over 5 in the j direction. And so if we distribute minus 1 over 25 to all of this, what are we going to get? We're going to get, well, you can see that we're going to have the 1 over 9 and the the minus 1 over 25 times 3, so that's going to be, well, let's just do it. It's minus 1 over 9 I minus 3 over 25 times 5 is 125 I. We're going to have to give these a common denominator. Minus 4 over 125 J. So now all we have to do is find a common denominator, right? So we can multiply this times 125 and this times 9. That's going to give me 120 minus 125 minus 9 times 3 is 27. All divided by 125 times 9 is going to be 1125. 1125. And then that's in the I direction. And then, of course, minus the 4 over 125 in the J direction. And if I add this up, I get finally that we have minus 152 over 1125 I hat minus 4 over 125 J hat. F sub 3, the force on 3 is going to be very similar to what we did here. We'll set it up again. Force on 3, so first we'll take the force of 1 on 3. That's going to be in both the positive x and y direction, so we'll keep that positive. The force of 2 on 3 is also in the positive y direction, so we'll keep that positive. And so I'm not going to do all of the work on this, but you would start out with well, the force of 1 on 3 is acting purely in the, 1 on 3 and 2 on 3. Let's do 2 on 3 first, because that's purely in the y direction, right? So that's going to give us 1 over 4 squared, or 1 over 16 in the j hat direction. And then we'll have 1 over 25 again, because 5 squared, that is the magnitude between Q1 and Q3, times 4 over 5 for the y direction, plus 3 over 5 for the I hat direction. And if we work all of this out, in the end we should get that it's 3 over 125 I hat plus 189 over 2000 in the j hat direction. Yeah, and so that's it. It's a little bit tricky. It's a good bit of work you have to do. You have to be careful, especially tracking your signs. But a little bit of patience, you should get through it, no problem. Okay, number 4. Calculate the magnitudes of the forces from problem 3. Okay. So I should have just left the work from the previous problem up here, but before we found that F sub 1 was equal to minus 152 over 1125 in the I hat direction. Remember, I hat is the x direction. Minus 4 over 125 in the j hat direction. That's F1. F2 we found was equal to, was 1 over, that was the easy one, right? Yeah, 1 over 9 in the I hat direction minus 1 over 16 in the j hat direction. And then F3 was 3 over 125 in the I hat direction plus 189 over 2000 in the j hat direction. Really should switch to x hat and y hat. Probably easier to read. So let's first calculate the magnitude of 1. So magnitudes are pretty easy to calculate. The magnitude of F1 is just going to be equal to the square root of the component squared. So we'll have minus 152 over 1125 squared. I hat dot I hat, so that just becomes 1, but I'll write it in. Plus minus 4 over 125 squared j hat dot j hat. And so you remember that dot products, right? I dot I is just equal to 1, and j dot j is just equal to 1. I dot j would be equal to 0, right? So no cross terms. And if I punch this into my calculator, square these, add them up, take the square root, this is equal to 0.139 newtons, provided that I punch things into my calculator correctly. Sometimes you make mistakes with the calculator, and that is unavoidable, but type it in a couple of times. Hopefully you'll get the right answer. F2, we would just square the terms 1 over 9 squared plus, I'm going to leave out the I dot I business this time because we know it's just going to be 1, plus the square of the y term is 1 over 16 squared, and that's going to be equal to 0.127 newtons. And finally, for the third force, the force on 3, the magnitude of it is, I guess I don't need all that much room, but 3 over 125 squared plus 189 over 2000 squared, and that's going to be equal to 0.0975. Yeah, and so if we look at the original picture, we had Q1, Q2, and Q3 on this right triangle. This was 3, this was 4, this was 5. The smallest force here says the F3. The force on 3 is the smallest. If we think about it, does that make sense to us? Well, it's pretty far away from charge 1, and it's relatively far away from charge 2. Whereas if we look at charge 2, it has relatively nearby, only a distance of 3 away, charge 1. If we look at charge 1, it also is within 3 of charge 2. So these two, right, should be the bigger forces, whereas this one should be the smallest, and so we see that it is. Now, why should force 1 be bigger than force 2? Well, the force on 1 is larger than the force on 2 because force 1 has a charge that's 3 away and 5 away, whereas force 2 has a charge that's 3 away and 4 away. So the force on 2 should be bigger. And is that what we got? No, we got the opposite. Hopefully I didn't make a mistake here. Let's think about my reasoning one more time. So the force on 1 is going to be bigger than, let's say, the force on 2. This kind of balances out. This guy is 4 away from a neighbor. So I don't know, maybe I typed some numbers in wrong, or maybe I just got the calculations wrong altogether. Maybe I could have made a numerical mistake somewhere along the way. Check my math, see if it looks good. Let me just double check, make sure my diagram is right. Yeah, that's the right diagram. Q1, Q2, Q3. Force on 1 seems to be the biggest. Well, I guess here's one way to think about it, right? The shortest distance between 2 points is always a straight line. And so charge number 1 does have the shortest distance to Q3. Well, not if you're over here, though, huh? I'm not sure. If you can figure out why the force on 1 is a little bit larger than the force on 2, then drop a comment in. Otherwise, I probably just made a dumb numerical error when punching numbers into a calculator. All right, on to the last problem. Okay, the last problem, problem 5. Find the charge on a single electron in hypothetical units of coulombs from the data below. So it gives us measurement number, charge, and you see these values start at 6.1, then 4.3, and then 4.3, and then 2.1, then back up to 6.1. So the first thing we want to do is reorder these charges, starting with measurement 1 will be 2.1, then we'll have a 2.3. The next one is probably 4.0, then 4.1, then 4.3, another 4.3, another 4.3, then a 6.1, a 6.1, and a 6.4. And if we reorganize those and then graph them, as shown here, measurement 1, 2, that's the first two, and we can see that they kind of split up into these 3 different bands, right? If we were to average these values, right, you can kind of get an average value with a measuring rod through like that. This one, you can kind of roughly see where it's going through, something like that. And then this last one is going to be something like that. Well, if we do that, we can actually do actual numerical values. So this one down here would be 2.1 plus 2.3 divided by 2 is going to be equal to 2.2. So that's this average value here, 2.2. If we add these points up, that's 4.0 plus 4.1 plus 4.3 plus 4.3 plus 4.3. Of course, you could have wrote 3 times 4.3 there. That would have been smarter. And divide by 5 measurements. That gives us 4.2. So this line here is 4.2. I didn't mean to put a dot there. It makes it look like a data point. And then this last one has 3 values in it. We have 6.1. Let's do 2 times 6.1 plus 6.4, I think. 6.4. And that is divided by 3. And that's going to be equal to 6.2. So we see that between this band and this band, and between this band and this band, we just simply take the difference. So we take 4.2 minus 2.2. That's, we'll say E equals 2. And here we have E equals 6.2 minus 4.2. It's again 2. But the difference between here and, say, the bottom band, of course, is 2E, right? So here, I guess the answer is that if we average these two values here, 2 plus 2 divided by 2, we get 2. So the amount of the electron charge in these hypothetical units of coulombs is 2 coulombs.